soils. Okay. Yeah. With respect to the usual types. Now, with respect to the general subgrade rating, they are normally considered as fair to poor. Huh? Okay. Yeah. So again, this is used by the DPWH. Okay. So if you look at the DPWH design guidelines, you can or the DPWH Blue Book, for example, you can find these tables there as well. Okay. Now, just a note here for the A-7 subtype, then it still has two subtypes. That's A-7-5 and A-7-6. Okay, so it can be considered as I hope you're seeing my cursor here. Uh, for A-7-5, in this case, the PI is less than or equal to the liquid limit minus 30. Okay, if you have that criteria, then that's A-7-5. If the PI is greater than the liquid limit minus 30, then that's considered as A-7-6. Okay, for the AASHTO soil classification. Okay. Okay. So to classify the soil according to this table, okay, this one here, this table, one must apply the test data from left to right. So that means we check first the leftmost classification, the leftmost type, okay, of material. Okay. Then if it will not satisfy the leftmost type, then we proceed next to the right, no? To the next material type. Okay. So by process of elimination, the first group from the left into which the test data would fit would be the correct classification. Okay. So for example, if I have a material, a test result, for example, then I check this one first, okay, this one here, and then it say, for example, it will not satisfy this one here, then I go to the next classification. If it will not satisfy, then I go to the next, and so on and so on. Okay. Then here from A-2 to 7, then we go next here. Then here, left, then going to the right. Okay. So starting from A-1 until A-7. That's how we check. Okay. So this is a figure here, which is figure 5.2 in your book. Okay, if you have your book. Okay. So this figure here shows a plot of the range of and the plasticity index for soils that fall into groups A-2, A-4, 5, 6, and A-7. That's this one here. A-2, okay, so take note, you have here the liquid limit and the PI, as well as the A-4 to A-7, no? Where their corresponding values of the liquid limit and the PI. So if we plot them here in this graph, wherein you have a plot of the liquid limit against the plasticity index, then this is where they belong. So in this region, you have the A-4 and A-2-4. Okay? In this region here, okay, so this region here, you have the A-6 and A-2-6 materials. And then in this region here, you have A-7-6. And then in this region here, you have these subtypes. Okay, and then in this region here, you have the A-2-5 as well as the A-5 material. Okay, so just to have um, uh, a quick view of where these materials fall with respect to the plasticity index. Okay, so you notice here that for the materials, it's based on this one here. Yeah? Okay, and 10. Okay, plasticity index of 10. No? So above 10 and below uh, 10. Okay. Yeah. Okay. Now, to evaluate further the quality of a soil as a highway subgrade material, one must also incorporate a number called the group index or the GI with the groups and the subgroups of the soil. Okay. Now, this index is written in parentheses after the group or the subgroup designation. Okay. Now, this group index is given by this equation here. I'm not sure if it is still equation 5.1 in your book. Okay, so this is basically the equation there. Okay, where this is now the group index. Then F sub 200 is the percentage passing through the number 200 sieve. Okay, and then LL is the liquid limit, and then PI is the plasticity index. Okay. Okay. So if you notice, this equation here has two terms. This is now the first term. Okay. And then this is now the second term. Okay. Now, the first term there is called the partial group index, which is determined by the liquid limit. Okay. And then the second term in the equation is the partial group index, which is determined by the plasticity. No? So here you have the LL, the liquid limit, and then here you have the PI. Okay. So here are some rules no? For determining the group index. For example, if this equation here would yield a negative value, then the GI, okay, so the GI here will be taken as 0. Okay? And then if the equation or the GI um, is actually is rounded off also to the nearest whole number. No? Okay, for example, if the GI is 3.4, then we round it off to 3. But if GI is 3.5 and above, then we round it off to 4. Okay, for the GI value. Okay, again, and also there is no upper limit for the group index. Okay. And then the group index of soils belonging to groups A-1, A-2, and A-3. That's this one here. Okay, so these groups here, okay, which are the granular soils. Okay, so these groups, the group index is always 0. Okay, that means no need to calculate. Okay, that's always 0. Okay, for the granular materials. Now, when calculating the group index for soils that belong to A-2-6 and A-2-7, okay, so that means this is excluded, no? This one here, okay, this is excluded. So only this 5, okay, only this 5, the GI is always 0. But for these two, A-2-6 and A-2-7, okay, uh, you have we use the partial group index in let's see in the second term. I think that's the second term, and this one here. So that's okay, that's this one here. No, we just use the second term, okay, to determine the GI. Okay. So in general, the quality of performance of a soil as a subgrade material is inversely proportional to the group index. So that means if the group index is 0, then that means you have these good materials. No? If you recall, no, these are good materials. No? This one here. Okay. Then as the group index becomes higher, then that means it will now have a poorer um, quality no? For the subgrade material. So then that means we should always try to aspire for 0, a value of 0, for example, or lower values. Okay. Okay, so I think that's for the AASHTO soil classification. Okay, so yeah. Now this time, let's try to discuss now the unified soil classification system. Okay, so the original form of the system was proposed by Casagrande, who also uh, de- designed the uh, the Casagrande apparatus for the Atterberg limits, for example. Okay, in 1942, during World War II, okay, for use in the airfield construction works undertaken by the U.S. Army Corps of Engineers. Okay, and then in cooperation with the U.S. Bureau of Reclamation, this system was revised in 1952. Okay. Now, at present, it is used widely by geotechnical engineers, for that matter. Okay, and then we also have the ASTM standards for this soil classification. That's the American Society for Testing Materials. That's ASTM D2487. No? So you can try to research on this if you like. Okay, and you have there the specific guide for this classification system. Okay, so the Unified Soil Classification System, or the USCS system, is given in table 5.2 in your book. That's basically this one here. If you have your book, you can also see this table. Okay, if you are more convenient in looking at your book. Okay, so let's go back to that later. So in this system, we basically have two general types. Now you have the coarse grain soils, and then you also have the fine grain soils. Okay. Now for the coarse grain soils, these are the gravelly and the sandy in nature, with less than 50% passing through the number 200C. Okay. Um, so kanina, we have, okay. So for Ashto, it's 35%, no? Ang ilang criteria, no? For the passing number 200C. 35 above and below. Now for the USCS, we consider 50%, no? Okay? For passing the number 200C. So if it is less than 50%, the scores grain, okay, soils. Now in this soil types, the group symbols start with the prefix of G or S, where G stands for gravel or gravelly soil, and S stands for sand or sandy soil. Okay. Now, for the fine grain soils, these are basically those soils with 50% uh, or more. Okay, 50% or more passing through the number 200 sieve. Again, the number 200 sieve is the 75 micron diameter soil particle. Okay. So for the fine grain soils, the group symbols start with prefixes of M, which stands for inorganic silt, and then C for inorganic clay, and then O for organic silts and clays. Okay. We also have the symbol PT, which is used for peat or muck or other highly organic soils, no? Which we're in normally, if we have this on site, we normally try to remove these organic soils. No, we don't like these organic soils. Okay. As far as engineering purposes is concerned. Okay, but for agricultural purposes, they can be used. Okay. Okay. So aside from the symbols here, I have G, S, M, C, and O, PT. We also have the symbols here for further classifications. W stands for well graded. P stands for poorly graded. If you recall the grain size distribution curve, we have the well graded distribution curve, and then you also have the poorly graded distribution curve. Okay, I just try to recall them. And then you also have the L and the H. Okay, where L stands for low plasticity. Okay, that's liquid limit less than 50. That's low plasticity. And then for liquid limit more than 50, that means you have high plasticity. Okay. Again, we don't like high plasticity materials also as far as engineering um, objectives are concerned. No? Okay. 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 So let's see. Um, okay. Looking at this table now, okay, this table 5.2, if it is not clear with you, you can also refer to your book. Okay, I'm not sure if it's still 5.2 there, in your book, but this is the table you can see. Okay, so again, you have here two, let's just try to go over this table here. So again, you have two general types. No? You have the coarse-grained material, if you're seeing my cursor, this region here. Okay, and then you have the fine-grained material. Okay, so for the coarse-grained material, this is more than, okay, these are the materials with more than 50% um, of number 200 sieve retained. No? Ang nabilin, no? Ang nabilin sa sieve. No? Kaya kanina mo sieve naman yung screen, di ba? So ang katong nabilin sa screen, sa number 200, okay, or yeah, more than, no? If more than 50%, no? Okay, retained on number 200, then we call them the coarse grain soils. No? So basically that includes the number 10, number 40, no? As well, no? And um, number 4 as well, no? Okay, so these are the coarse grain materials. Okay. Now, for the fine grain materials, these are the materials with 50% or more passing the number 200C. Yeah? Okay. Okay. So let's have the coarse grain soils first. Now, for the coarse grain soils, you have two general types. You have the gravels and the sands. Okay. So in this between the two, let's now try to check the number for sieve. Okay, so if you try to recall, the number for sieve is equivalent to 4.75 millimeters. Okay, so if more than 50% of the coarse fraction is retained on the number for sieve, then we consider it as gravels. Okay, but if 50% of more of the coarse fraction passes the number for sieve, then we call it the sands. Okay. Now, focusing on the gravels, you have here two general types. Okay. You have the clean gravels and then the gravels with fines. Okay. Now, for the clean gravels, these are this one here has less than 5% fines. Okay. So uh, when you say fines, um, these are usually the number 200C. No? They are also considered the fines. Okay. Um, so here there's a footnote A. No? Okay. Sorry if you're seeing my cursor A. So let's see the footnote here for this clean gravels. So for gravels with 5 to 12%, because this is less than 5, and take note here it's more than 12. So there's no between. No? So for gravels with 5 to 12% fines would require dual symbols, okay, such as we try to pair, no? We try to pair the two, okay, this one here. either GWGM or GWGC or GPGM or GPGC. Okay. But for gravels with fines, which means that it has more than 12% fines, okay? So you have here again the footnotes, okay? A and B, okay? Uh, yeah, I think this should be B as well, no? Oh, sorry. Yeah, yeah, A and D, sorry. Um, so, okay, A, we already discussed that. Then here, there's a D. So what does D say? Um, okay. Okay. Before we go to D, uh, here you have the descriptions first. Not the descriptions. Okay. For example, in the clean gravels, if the CU is greater than or equal to 4, okay. Yeah. Um, and then the CC is greater than or equal to 1, but less than or equal to 3. Okay, if you recall, this is the uniformity coefficient. Okay, this was our first lesson. This is the uniformity coefficient, and this is the coefficient of gradation, wherein these are the formulas for that. If you can see my cursor here at the bottom. Okay, these are the formulas for that with respect to D10, D30, and D60. So, which means that if you satisfy this one, for clean gravels, then we call it, or we have the symbol GW, where G stands for gravel, W stands for well graded. So that means this is a well graded gravel. Okay. Yeah. Now, again, for the clean gravels with less than 5% fines, if the CU is less than 4, or if the uniformity coefficient is less than 4, and or the coefficient of gradation is less than 1 or greater than 3, then we call it a poorly graded um, material. Okay, so that's G means gravel, P means poorly graded. Okay, that's for the case of clean gravels. No? Okay, now for the case of gravels with fines, okay, with more than 12% fines, then it has again two criterias. If the PI, okay, if the PI, okay, so considering you have 12%, more than 12% fines, if the PI is greater than 4, okay, or plots below the A line, okay, in figure 5.3, where's the figure? Okay, this one here, no? This is again the plasticity chart, which we just discussed last meeting, okay? So if the PI is less than 4 or plots below the A line, okay, below the A line, this one here, this is your A line, okay, then we can call it if you recall, M means silty. No? So we call it a silty gravel. No? That's GM. Okay, that's a silty gravel. Okay. But if the PI is greater than 7, and and plots on or above the A line in this figure, where this is the A line again, okay, then we call it GC, no? Where G means gravel, C means clay. Now this is silty clay, okay, a clayey gravel, okay. Okay, so here there's a footnote D now. Now you notice that here the PI here is less than 4, and here the PI is greater than 7. There's no between. No? How about if your PI is between 4 and 7? So that's the footnote here, that if the PI is greater than or equal to 4, but less than or equal to 7, and plots in the hatched area in figure 5.3. Now this one here, for example, hatched, this is the hatched area. Okay. Um, then we can use a dual symbol. Okay, a dual symbol GCGM. Okay, GCGM. Um, okay, that's GCGM here. Okay, or SCSM. Okay, but now let's go to the SANS. No, that's for the case of SANS. Okay. Um, so I think we have already explained this footnote A and D and C as well. Okay. Mm. Now, in the case of SANS, so we have here two types. Okay, you have the clean sands as well as the sands with fines. Okay, now the clean sands, this is less than 5% fines. Okay, the fines is usually the number 200 sieve. And then for sands with fines, these are materials with more than 12% fines. Okay, now in the case of clean sands, okay, clean sands, less than 5% fines, for a CU greater than or equal to 6 and C sub C, no? The uniformity coefficient and the coefficient of gradation, okay, is less than 1, less than or equal to, or sorry, greater than or equal to 1, but less than or equal to 3, okay, then we call it a well-graded sun. No? Okay, well-graded, S means sun, no? Well-graded sun. But if the CU is less than 6 and or the CC is less than 1 or CC is greater than uh, 3, then we call it a poorly graded sun. Okay. Yeah. Now, for the suns with fines, with more than 12% fines, okay, if the PI is less than 4 or plus below the A line, then we call it a silty sand, just like same here. This is just silty gravel, but this one here is silty sand. Okay. And then the same criteria, then we just call it a clayey sand instead of clayey gravel. In the case of sands with fines. Okay. Now, for the fine-grained soils, okay, it has two general types. You have the silts and clays with liquid limit less than 50, and then you have the silts and clays with liquid limit more than 50. Okay, 50 or more. No? Okay, 50 or more. So for the silts and clays, either in these two, you have two classifications, further classifications. You can either have inorganic or organic material. Okay. In the case of inorganic material, okay, then you have here the PI. If the PI is greater than 7 and plus on or above the A line here, above the A line of the plasticity chart, okay, then we call it a low plasticity clay. Okay, C means clay, L means low plasticity. Now, if the PI is less than 4 or plus below the A line in the plasticity chart, then we call it the low L, the low plasticity silt. No? M means silt. Okay. And then for if under this criteria, if it is organic, okay, then it must satisfy this formula here with respect to the liquid limits. Okay, or it is in the OL zone in the plasticity chart. Yeah, this one here, the OL zone in the plasticity chart. This one here. Okay, that's below liquid limit of 50. Okay, below 50. Okay, then we can call it the OL. Okay, yeah, OL material. No? Okay, that's the organic. Uh, okay, maybe the organic cells. Okay, sorry, the low plasticity organic materials. Okay. Okay. Now, for the seals and clays with liquid limits above or 50 or more, Then again, you have here the inorganic and the organic material. For the inorganic, in the case of inorganic material, if the Pi plus on or above the A line, okay, so on or above the A line of the plasticity chart, okay, then we call it a high plasticity clay. H means high plasticity, C means clay. If the Pi plus below, no, below the A line of the plasticity chart, okay, then we call it a high plasticity. H means high plasticity, M means cell. So we call it a high plasticity cell. Okay. So in this case, if it is organic material, okay, then we can, or if it is found in this range here, okay, okay, in this region here with liquid limit above 50, then you have your OH here, okay, this is either inorganic or organic, no? Okay, so you have here the OH materials, okay, um, but normally in practice, for example, we normally do organic tests as well, no? Organic test, okay, in such a way that we can check how organic the material is. We have a certain uh, cutoff for the organic content in such a way that okay, we can still consider it as maybe inorganic or yeah, or highly organic material. Okay. If the site is highly organic, then we try to do soil replacement as part of our ground improvement works. Now, for the highly organic soils, so these are basically the primarily organic matter, dark in color, and it has an organic odor. No? So, medyo may amoy, no? Pag highly organic soils. No? So, these are the PT materials. Okay. So here there's just a footnote. No? In the case of this one here, for the CL and ML, there's a footnote E. If the PI, because here this is greater than 7 and less than 4, there's no values in between. So if the PI is greater than 4, but greater than or equal to 4, but less than or equal to 7, I hope you're seeing my cursor here at the bottom. And plus in the hatched area in figure, this plasticity chart, this one here is the hatched area, okay? Then we can use a dual symbol, okay? CL, ML, okay? And then same also here, no? Okay? For this one also, the same criteria here. It falls within this range, then you can have SCSM material. Okay, SCSM. Um, and then here, for the clean sands with less than 5% fines, okay, if the sand contains 5 to 12%, okay, 5 to 12%, because this is less than 5, this is more than 12. But if the fine contents is between 5 to 12, okay, then that would require dual symbols. So then we can combine SWSM or SWSC or SPSM or SPSC. And that's this one here. Depending on which one will be satisfied. Now, later on in the examples, we will have that. Okay. So if this one is satisfied and this one is satisfied, then you can have SWSM. Okay. If this one here criteria is satisfied and this one is satisfied, provided you have fine contents between 5 and 12, yeah, between 5 to 12, okay, um, uh, then you can combine no, the symbols. Okay, that this is what this footnote means. Okay, as well as this one here. Normally, in practice, we send the materials to the lab, and then it will be the lab who will be determining this one. No? Okay, so Again, if for example, in large projects, we usually have 10 boreholes at 30-meter depth. Okay. So that means if we usually get samples every 1.5 meters, then if this is 30-meter depth, you have 20 samples times 10 boreholes, that's 200 samples. So that means you will have to do these classifications 200 times, okay, in the lab. Okay. Okay. So for proper classification, according to this system, okay, so now some or all of the following information must be known. Okay, so first we need to know the percent of gravel. Okay, that is the fraction passing the 76.2 millimeter sieve and retained on the number for sieve. Okay, that's the 4.75 millimeter opening. Okay, then you have the percent of sand, that is the fraction passing the number for sieve and retained on the number 200 sieve. Okay, that's the 75 micron opening. And then you have the percent of silt and clay, which is the fraction finer than the number 200 sieve, or these, yeah, again, the 75 micron opening. Okay, we also need to know the uniformity coefficient, Cu, and the coefficient of gradation, okay, Cc. And then we also need to know the Atterberg limits, huh? Okay, the liquid limit as well, and as well as the plasticity index of the portion of soil passing the number uh, 40 C. Okay, okay. So the group symbols for the coarse grain gravelly soils are this one here. So I guess basically you already know the meaning of this. Okay, I hope by now you already know. Okay, so again, G is gravel, W is well graded, P is poorly graded, M means silt or silty, C means clay or clay. Okay. Then for the group symbols for the fine grain soils, so we have this one here. So again, C means clay, M means silt, L means low plasticity, and then H means high plasticity. Then PT means peat or muck, highly organic soils. Okay. Now, okay, more recently, the ASTM D2487 created an elaborate system to assign group names. Group names to these soils, because this one here are only symbols. Okay, so these names are summarized in figures 5.4, 5.5, and 5.6 in your book, if you have your book. Okay, so basically these are figures of 5.4, 5.5, and 5.6 in your book. Okay, later on, we'll be using these tables in the examples. Okay. Now, in using these three figures, one needs to remember that in a given soil, um, defined fraction is defined as the person passing the number 200 sieve, just like this one here. Okay, defined fraction. Okay, it's the one passing the number 200 sieve, while the coarse fraction is the percent retained on the number 200 sieve. Okay, that includes number 4 and number 40. Okay. Now, the gravel fraction is defined as the percent retained on the number 4 sieve. Okay, that's the number 4 sieve. Okay, please take note of that. And then for the sand fraction, this is defined as the percent retained on the number 200 sieve, or that's equivalent to 100% minus the percent passing the number 200 sieve, depending on what is given. Okay. Um, this is also termed as plus. No? This is also termed as plus number 200. Okay. In some problems, you will see those terminologies. Okay. So minus the percent retained on the number for C. Okay. So that's the percent gravel. Okay. Yeah, percent gravel. Okay. So that's this one minus the gravel fraction. Huh? Okay. That gives you the sand fraction. Okay. Because you notice here, um, see here in the classifications, you need to check further the percent sand and the percent gravel. Okay, here you have the percent sand and the percent gravel. So we need to know these ones here. Okay, yeah. Okay, so this is just to give you an idea of that. Um, so basically, everything that I explained here in this table, they are just being summarized actually here, as well as here, and as well as here. Okay? So, kumbaga, when you do this later on, kinanya mismo ang inyong tanawon, no? Okay? As your guide. Okay? Anyway, we'll use them in the examples. Okay? Okay? Okay. Now, in the unified system, the gravity and the sandy soils, uh, uh, just a comparison between the unified and the AASHTO systems. Okay. Now, in the unified system, the gravity and the sandy soils are clearly separated, while in the AASHTO systems, they are not clearly separated. The 8-2 group in the Ashton system in particular contains a large variety of source symbols like this one here, okay, well-graded gravel, silty sand, and high plasticity clay and others that are used in the unified system are more descriptive of the soil properties than the A symbols used in the Ashto system. So just to compare the two systems. Now, the classification of organic soils such as OL, OH, and PT is provided in the unified system, while in the ASH2 system, there is no place for organic soils because it cannot be used anyway in highways. Okay. Now with respect to organic soils, peats usually have a high moisture content, a low specific gravity of soil solids, and a low unit weight. Okay. So I think this one here, we have examples of different types of peat materials. These are the scanning electron micrographs or the SEM um, screenshots, no, of these 4 peat samples. Okay, this one for the Middleton peat, Waupaca peat. Then this is yeah, so this is a French. This is probably a French peat. Okay, then you have here the portage peat. Okay, yeah. So just looking at them microscopically, no? Okay, using the SEM equipment. Okay. Okay, now just to have some idea of the moisture contents, no? The unit weights and the specific gravities of these peats. No? Now you can see here that the moisture contents for all the peats or generally for peat materials is higher than 100%. Okay, which means that for peat materials, water is occupying more than the um, solid materials, no? Okay, with this moisture content. Okay, the unit weights are generally lower. Okay, normally we have for normal soils, say um, between 12, I guess, no? Between 12 to 21. No? That's the usual unit weight. So this one here is generally lower. Okay. And then for the specific gravities, normally we are around 2.65 to 2.9, for example. But this one, the specific gravity is quite low. No? That's the difference between peats as compared to the other soil materials. Okay. Okay. Now, this guy, Liu, in 1967, okay, he just tried to compare, no? Between the AASHTO system and the USCS systems. No? Okay, so which means that in his comparison, okay, for example, if you have A-1-A, so most probably this is equivalent to GW and GP, a well-graded gravel or a poorly graded gravel. Okay, then possibly, okay, this is the most probably, no? This is the one. And then possibly this is well-graded sand or poorly graded sand. Okay, but in these materials, it is possible, but improbable. No? It is improbable that it is a silty gravel or silty sand. No? Okay, that is just his comparison. Just to give you an idea how Liu tried to compare the materials in the AASHTO and the USCS systems. Okay. Okay. So yeah, just to continue, he just compared uh, this one. No? So this one from AASHTO to USCS system, and then this one from USCS system to AASHTO. No? So he just compared it, no? Just to give us some idea. I think this is also in your book. So if you can buy an electronic copy of the book, or yeah, it would be better for you. Okay. Again, all of these are just in the book. Okay. Okay. I think that's it. I think we can now have some examples. Okay. So let us now try to use those tables. No? Okay. So for example, here, you have the results of the particle size analysis of a soil are given here. You have the percent passing number 10 sieve is 42%. The percent passing number 40 sieve is 35%. And then the percent passing number 200 sieve is 20%. And that's based on this sieve shake test. Now this is what you measure, okay? Or rather what you calculated, no? From the for the grain size distribution curve, okay? And then you also did in the lab, you did some um, Atterberg limit test, wherein you had the liquid limit and, sorry, this is not PI, but rather the plastic limit. This is the plastic limit of the minus number 40 fraction, or that's the materials passing the number 40 sieve. Okay, so that's basically this one here, no? The 35 and the 20. Okay, that's the minus number 40 sieve. Okay, so for this one, the liquid limit is 25, and then the plastic limit is 20. Okay, in such a way that the PI, no? If you're seeing my cursor, the plasticity index is the liquid limit minus the plastic limit, or that is 25 minus 20, then you have a PI of 5. Okay. Okay. So again, if we check the table, if the material is less than 30, if the percent passing number 200 is less than 35, then we consider it a granular material. So in this case, if we are to classify this material according to the AASHTO, the percent passing number 200 is less than 30, I'm sorry, yeah, is less than 35. Okay, that's 20, less than 35. So then we use this table for granular materials. We don't use the other table for silk clay materials. Okay, so we use this one. Okay. Okay. Sorry. So now looking at table 5.1, okay, um, since the plasticity index is five, then let's see. If the PI is 5, then I think the A2 will not be possible, no? Because here the PI, uh, oh yeah, this one is okay. No? Okay, so maybe yeah, let's just start here. No? Um, so if we look at, again, if we try to interpret this table, we always start from the left. Okay, then by elimination process. Okay, so let's start. Uh, uh, okay, for A-1-A, let's see. Uh, the person passing for number 10 is 42. Let's see. Okay, person passing is 42. Okay, that's okay here. I did not exceed 50. Then number 40 is 35. So here we don't pass, no? Because this is maximum 30. Okay, so it doesn't qualify. So then we go to the next classification. So here there's no criteria for number 10, so it's okay. This value is okay. For number 40 it's 35, so it's okay here. This is maximum 50. For number 200 it's maximum 25. What's the number 200 here? It's not okay, it's just 20. So we satisfy this one. For the liquid limit, there's no criteria. For the PI, maximum of 6. So here, our PI is 5. Okay, so that's this one. Maximum 6. Okay, maximum. So that means we are okay for, we have satisfied A-1-B criteria. No need to proceed here. Okay, so the moment you have already satisfied this criteria, then you stop there for your classification. No need to proceed further to the right. So that means this material, okay, based on this data, can be considered as A-1-B. Okay, then just a guide for this soil material type, the group index of the soil is automatically 0. Okay, so that's why here in parentheses, this is the group index. You have here 0. Okay, if you recall the guide, where was that? Where did we have the guide again? Yes, this one. That's A-1-B. The GI is always 0. Okay, that means for these first 5 materials, the GI is always 0. No need to calculate. Okay, then let's have another example. Okay, so in this example, 95% of a soil passes through the number 200 sieve and has a liquid limit of 60 and a plasticity index of 40. Okay. So we are asked to classify the soil by the AASHTO system. Okay. So based on the data, okay, so based on what you got from the lab, for example, so 95% of the soil is or passes through the number 200 sieve. Okay. So that's the minus, no? Minus number 200. It's also called minus uh, number 200. Okay. Um, so since this 95% is greater than 36%, so that means we can use this table here for the AASHTO classification under the silt clay materials, where in more than 35% of the total sample passing number 200. In this case, we have 95%, so it's more than 35%. Okay. So then it is a silt clay material. Okay. So again, starting from left to right in the table. Okay, so let's see. That's 95%. Uh, in a liquid limit of 60%. And PI of 40. Okay. So, okay, all of them. Okay. So it satisfies because these are all 36 minimum. But for the LL, the liquid limit and the PI, liquid limit is 60, PI is 40. Okay. So liquid limit is 60, so that means it will not satisfy this one. It will satisfy this one. But for the PI is 40. Nope, it will not satisfy this one because this is only maximum 10. So we go here. This will not be also satisfied because this is maximum 40. Our liquid limit is 60. Then, okay, so we now go to the last. No? So here we have 60. Our liquid limit is 60, satisfying this one because this is only this is 41 minimum. Minimum 41. And then our PI is 40. So that satisfies this one. Minimum of 11. So that means we have a clayey soil material according to the AASHTO. Okay. Now take note, for A-7, we have two subtypes, no? Either A-7-5 or A-7-6. So then for these two criterias or subtypes, let's now try to compare the PI against the liquid limit. Okay. So if we now try to compare, you have the liquid limit minus 30. So the liquid limit is 60 minus 30 is equal to 30. If you compare that to the PI, which is 40, then the PI is greater than this term here. So in that case, PI is greater than this term here. So that means we have an A-7-6 material. No? So that's this one here. That's A-7-6. Okay. Then we just calculate for the GI or the group index. Okay. So we just simply substitute here the percent passing number 200. So that's 95%. Then the liquid limit is 60. And then the plasticity index is 40. So just substitute it here. Then you get a value of 42. So then you put that in the parentheses as your group index. Okay. So it has a higher value as compared to 0. Okay, so this is how we can use the AASHTO classification system. Do you have any questions or clarifications so far before we go to the examples for the USCS system this time? Okay, if there's none so far, okay, let us now go to the example for the USCS system. Okay. Okay. So here we have some results of the particle size or the grain size analysis test of the soil, which gives us the percent passing through the number 10 sieve. Okay, let's see. Okay. So then the person passing in the number 40 sieve is 80, and then the person passing through the number 200 sieve is 58. Here also, the liquid limit and the plasticity index of the minus 40 fraction, that includes this one and 200, of the soil are 30 and 10. Okay, so LL is 30, PI is 10. So from this data that we got in the lab, we are asked to classify the soil by the unified soil classification system. Okay. So here we see that the percent passing number 200 is 58%. Okay, so if we now try to look at this table here, which we just discussed earlier, that's 58%. So that's yeah, 50% or more passing the number 200 sieve. So that's 50%. So that means we consider it as a fine-grained soil. Okay, so that's here. Okay. And then referring now to the plasticity chart, okay, we have the LL equal to 30 and PI equal to 10. Okay, so let's see. Based from the plasticity chart, LL equal to 30, that's this one here. PI equal to 10. Okay, then most probably this is um, can probably OL or CL. Okay. So in this case, yeah, we classified it as CL, presuming it is not an organic material. It is an inorganic material. So that's a CL. Okay, that means it is low, L means low plasticity clay. Okay, okay. Now, so to determine now the group name, no? The group name, no? Because this is just a symbol. To determine now the group name, so we refer to these figures here. Where's that? So we can now refer to this figure. Okay. So here we see that the liquid limit is less than 50. That's only 30. Then we presume that it is inorganic. Okay. Let's assume we know, no, that's inorganic. We have done some organic tests. It's inorganic. And then the PI is 10. Yeah, that's 10. So that's greater than 7. So that means we are here. Okay, we are here. That's CL. So we are following this path. But for to classify the CL further, no, to give the group name, so that means for the CL type of material, for the low plasticity clay type of material, you basically have 1, 2, 3, 4, about 7 group names. No, 7 group names. Okay. So here let's try to check further the plus number 200C. No? Plus number 200C. Okay, so let's see. Where is that? Okay. Mm. Okay. So again, to recall, the person passing number 200 sieve is more than 30%. Okay, 30%. Um, so and so the person passing number 200 sieve is just the same as the plus number 200. No, it's just the same. No? Plus number 200. So in this case, the person passing number 200 sieve or the plus number 200 is 58. So that's greater than 30%. No, it's not less than. Okay, so that means we go to this path. Okay, so this one here, we go to this path, not this one. So with this path, again, we need to check further, no? The person sand and the person gravel. So going back here, so for the percent of gravel, it is zero. Why? Because if we try to recall, the gravel fraction is the percent retained on the number for sieve. Okay, the percent retained on the number for sieve. Let's see. Do we have a number for sieve? So here, you notice in the data, the number 10 sieve is already 100%. That means all the materials that you put in the sieve, in all the sieves, okay, starting from sieve number 10, followed by sieve number 40, followed by sieve number 200 at the bottom, then the pan. We notice that all of them pass number 10. That's 100%. That means nothing is retained. So how much more for the number 4 sieve? Because number 4 sieve is a larger diameter than the number 10 sieve. I think number 4 is 4.75 millimeters. Number 10 is, I think, about 2 millimeters. Now, do we have that table? Let's see. Oh, where was that? Let's just see. Okay, here. So number 4 sieve is greater than or has a bigger opening than the number 10 sieve, no? Which is just 2 millimeters. Okay. So that means the percent of gravel is zero. Okay. Now, for the percent of sand, let's again recall what's again the definition of sand. So the percent of sand, that's your sand fraction. That's the percent retained on the number 200 C. Okay, so that's um, okay, so that's percent retained number 200 C. Okay, so let's see. So that's when you say person retained number 200 sieve, so that means if you're given the person passing number 200 sieve, that is um, uh, that's that's 100% minus the person passing number 200 sieve. Huh? That's equal to the person retained on the number 200 sieve. Okay. So again, what is given here is sorry. Okay. What is given is 58. Huh? That's the person passing number 200 sieve. Okay. So if you want to get the person retained number 200 sieve, then that is 100% minus 58. Okay. Yeah. So this is the person passing. Okay. So 100 minus the person passing will give you the person retained. Huh? That's this one. Huh? Okay. And then minus the percent of gravel, which is zero. So that gives you 42%. Okay, 42%. Okay. So that means the percent of sand is greater than the percent of gravel. So that means here we have mm, this criteria here. Okay, this criteria. So that means we follow this one here. Okay, we follow this one. So moving further, so then you have to check again if you have less than 15% gravel or greater than 15% gravel. Okay. So in this case, our percent gravel is zero. So yeah, it's less than 15%. So that means we follow this path. So finally, our group name is a sandy lean clay material. Okay, sandy lean clay. So in this figure, so that is this one here. No, so basically we follow this path. From here, we go here. From here, we go here. Then CL. Then we follow this path. And then here. And then follow this path. Finally, you arrive at a sandy lean clay material. Okay. And then the rest there, you have those group names. Okay. 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 So let's have another example. Okay. Uh, okay. So here for a given soil, we have here the data. So the percentage passing number for sieve is 70, whereas the percentage passing number 200 sieve is 30. Okay. Then with the liquid limit of 33 and the plastic limit of 12. Okay. So we are asked to classify using the USCS system and then try to give the group symbol as well as the group name. Okay. So again, you refer back to the table. Again, this one here. So the person passing number 200 is how much? That's 30. So that is, uh, yeah, so that's um, less than 50%. No? Less than 50% passing number 200, or that's equivalent to, if that is 30% passing number 200, that's equivalent to 70% retained, right? 70% retained. So that means it is more than 50% of the retained on number 200. Okay, so that means we can classify it as a coarse grain material. Kanina is fine grain man, no? So this time we have a coarse grain material. Okay, so for the moving on, we have the coarse fraction. Okay, so if you try to determine the coarse fraction again, how do we define the coarse fraction? The coarse fraction is the percent retained on the number 200C. Okay, so that is percent retained number 200. So the coarse fraction is percent retained. So that is equivalent to 100% minus the percent passing. Okay. 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 So that means 100 minus 30 is 70%. Na? Okay. This is now the percent retained na? In the number 200C. Okay. So that's the coarse fraction. Okay. And then with the coarse fraction, we want to determine the gravel fraction. Again, the gravel fraction, we define it, if you're seeing my cursor, that's the percent retained on the number 4C. Okay. So, so here we have the percent passing through the number 4C. Okay. So that means if you have 100% material, okay, so what is left is the percent retained. Okay, so that means you have the total 100% minus 70 percent for the percent passing number 4C will give you the percent retained on the number 4C. Okay, which is 30%, and that is your gravel fraction. Okay. Yeah. Okay. So yeah. Okay. Now, so here, we need to know, since we know already know that this is coarse grain soils, so we need to know if we have gravels or sands. No? So let's now try to check the coarse fraction retained on number 4 sieve. Okay, so here, the coarse fraction, okay, so that's 70%, right? Okay, see, okay, sorry, um, sorry. Okay, so that means, so this one, so that's more than, let's see if it's more than 50%. Okay. Mhm. Okay, so here we have 50% of course fraction passing the number for C. Okay, so let's see. Ah, so that's this one here. More than 50% or more of the course fraction passing number for C. Okay, so we have more than 50%. Okay, so that means that's actually um, this one. Okay, 70%. No? Okay, of the course fraction. Okay, passing now number for C. Okay, so that means we have here um, a sandy material. No? We have a sandy material. Okay, so we follow this one here. Now, next, we need to know if we have a clean sands or a sands with fines. Okay, a clean sands or a sands with fines. Okay, so let's see. So for the number 200, okay, what's the amount again? That's 30%. Okay, that's 30%. That's more than 12%. That's more than 12%. So that means if you look at the table, so it would fall under this one. No? It would fall under this sands with fines. Okay. So with that, we need to check now the PI. Okay, we need to check the PI. So if it is less than or 4 or greater than 7, what's the value again for PI? The PI is that's 33 minus 12. That gives you a PI of 21. Okay, PI of 21. So if you look at the graph, oh, we don't have the graph anymore here. So that's anyway, that's PI of 21. That's greater than 7. Okay, and then if we have the where's the consistency chart? Yeah, this one here. PI is 21. Okay, so yeah. Okay. Yeah. So that's somewhere here. Okay. Okay, so that means the group symbol is this one here. So from here, from coarse grain, we went to sands, and then we went to sands with fines, and then we have the PI greater than 7. That leads us to SC, or a clay sand material. SC. This is now the group symbol. Okay. Next, we need to find the group name as well, the group name. Okay. Now, for the group name, okay, we already have the SC. We already know it's SC. So basically, we look at this table. So we have SC. We have already identified that it is SC. So we need to check the percent gravel. We need to check the percent gravel. So earlier, we identified or we calculated the gravel fraction. Okay, the gravel fraction is 30%. Okay, that's 30%. So uh, it is greater than 50%, greater than 15%. Okay, so that means we go to this path. Okay, in the table, SC is greater than 15%. So we have a clay sand with gravel. Okay, so this one here, a clay sand with gravel. Okay. Okay. Now, how about if you have a dual classification system? Okay. Uh, okay. So let's say, for example, here, okay, this one is SC. This one is okay. So, for example, this problem here. I'm not sure if we still have time, but let's just try to discuss soil A. No? The soil A. Okay. Now, so in this problem, in figure 5.9, this one here, it's giving you the grain size distribution of the two the two soils, the liquid and the plastic limits of minus number 40 C fraction of the soil. Okay. Um, and then you're also given the liquid limit and the plastic limit. Let's just focus first on soil A. Okay, soil A. And then we have here the grain size distribution curve with the corresponding values for the D10, D30, and D60. Okay. Okay. So, um, so for soil A, okay, so we are given the grain size distribution curve, which indicates that the person passing number 200 is 8. Let's see. Okay, so this is soil A. No? This is the graph or the grain size distribution curve for soil A. This is the grain size distribution curve for soil B. No? Okay, soil B. Now, for soil A, if this is the number 200C, if we project it down, okay, the person passing number 200C, that this is number 200 is somewhere here. Now, this is 0.075 millimeter diameter. Now, this one here, that's 75 microns. That's your number 200C. So if we intersect that to the graph or to the grain size distribution curve, then that will give us a value, okay, let's say about 8, okay, according to the book. This is 8, this is 8, sorry, this is this is 8. So we have a person passing number 200 is 8, okay? So in that case, according to table 2 again, um, so we have, um, sorry, uh, sorry, okay. So according to table point 2, we have person passing number 200 is 8. So that is equivalent to 92% retained. No? Okay. 92% retained in the number 200C. Okay. So so that is more than, no? Okay. That is more than 50% of retained in the number 200C. Okay. So that means we have a coarse grain soil. Okay. So we didn't focus on this one here. No? Okay. Let's forget about the fine grain soil. Okay. Then also from figure, from this figure here, okay, the percent retained on the number for sieve is 0. Why 0? Because number for sieve is equivalent to 4.75. But if we look at the graph, the maximum particle diameter is only 1 millimeter. That means 100% has passed the number 4C. No? Okay. Yeah. So that means the percent retained on number 4C is 0. Okay. So if the percent retained number 4C is 0, okay. So yeah. If the percent retained on the number 4C is 0, then that means, yeah, you have 100%. No? You have 100% passing. Okay, so that means it belongs to SANS. No? Okay? That's more than 50%. No? Passed. Okay, because nothing is retained, no? On the number 4 SIP. So that means we have sand material. Okay, so then let's check if we have clean sands or if we have sands with fines. No? So let's check the number 200 sieve again. So how much is the number 200 sieve? The number 200 sieve percent passing is 8. Okay, 8. So let's see. So 8 is not less than 5. It is also not more than 12. Okay. So that means it would fall under this one here, under this footnote. Okay. It is between 5 to 12. Okay. So that means we can either have one of these these dual symbols here. Okay. Yeah. So then we need to check both. We need to check the uniformity coefficient and the coefficient of gradation as well as the PI. Okay. So now let's go back. Okay. So to get the uniformity coefficient as well as the coefficient of gradation, we need to determine the D10, the D30, and the D60. Okay. So from the grain size distribution curve, okay, this is now your D60. If you project it, D60, that's 60% finer, no? D60. So D60 is this one here, project it down. So that's about 0.135. Okay, that's according to the book. Okay, then for D30, that's the 30% finer. So the diameter for that, if you project it down, then that's about uh, 0.12 according to the book. Then finally, your D10 is about, that's the 10% finer. That's this one here. 10% finer, then project it down. That's your corresponding D10, which is about 0.085, not just above the 75 microns or the per 200 C. Okay. So now that we have these values or this diameter, sorry, this is millimeters. No? Okay. Uh, yeah, this is millimeters. No? Okay. So substituting the values in the formulas, okay, for the uniformity coefficient and the coefficient of gradation, then we have the CU less than 6 and then CC greater than 1. So let's go back to the table. That's a CU less than 6. Okay, so it satisfies this one. But CC is greater than 1. Okay, so it doesn't satisfy this one nor this one. No? Okay. Um, yeah. But anyway, this is and or. No? And or. In this case, we can use the or. So that means we satisfied this one. No? Okay. C is less than 6. Okay, so that's SP. Okay, that's SP. Okay. Then we also need to check the PI. Okay. So the PI, okay, what's the given again? The given is for soil A, LL is 30, PL is 22. So that gives you a PI of 8. No? That's 30 minus 22. That gives us a PI of 8. Okay, so PI of 8, if you go back to the table, okay, so PI is greater than 7. Okay, so that's, yeah, so that's a PI of 8. So that means, since you need a dual symbol, since the fines is between 5 to 12, no, it's not less than 5 and not more than 12, it's between 5 to 12. So we need a dual symbol. Now, since for the dual symbol, it satisfied this criteria and this criteria here, then that means we can combine SP and SC. Okay, so that means you have an SPSC material. Okay, so that's this one here, an SPSC material. Okay, so that's the group symbol. Okay. Now for the group name, let's now go to the chart. Okay, where's that SPSC? That's somewhere here. That's SPSC. Again, we need to check the percent gravel. Okay, again, the percent gravel is the percent retained in the number for sieve, or that's 100% minus the percent passing in the number for sieve. So let's check that. So here, the percent of gravel is 0. Why 0 again? Because number 4 sieve is equivalent to 4.75 millimeters. No? Okay, 4.75 millimeters. So that is um, If the highest diameter here is 1, okay, then that means everything has passed the a number for sieve or the 4.75 sieve. Okay, so nothing is retained in the number for sieve. So that means zero. Okay, nothing is retained. Okay, so again, by the definition, does the person retain number for sieve? That's your gravel fraction. Okay, so that means it is less than 15. So we don't use this pa, we don't follow this path. So we follow this path, no? Less than 15% gravel. So that means the group name is a poorly graded sand with some clay. Okay, with some clay because that's SPSC. Okay, so again in the table, that's SPSC. That's a poorly graded sand with clay or silty clay. That is now your group name. Okay. Okay. So I guess it's almost time. Okay. So yeah, I guess we can just end here with our lecture. I think my colleagues will just give you more examples next meeting, no, on Thursday. Okay. Do you have any questions or clarifications so far before we adjourn? Let me just stop share. I hope you can follow me um, well because it seems that I've been discussing maybe quite fast. I think.